Hey there, I am Rafael, and I am lithium-ion cell manufacturing guy. Throughout my career, I've designed cells, created manufacturing processes, and built entire factories. Right now, I am consulting on various projects, while also getting my startup, high-yield battery fab off the ground. Looking back, when I first jumped into the battery world, it was tough to find informative materials in manufacturing. Thankfully, things have improved since then, but I still feel like a lot of material out there either skims the surface or focuses too narrowly on specific topics. To really succeed in this field, you've got to pull together knowledge from different areas like electrochemistry, mechanics, electronics, manufacturing, and even statistics and automation. I believe this lack of a big picture view is one of the main reasons why so many battery projects stumble. In this video series, I am here to walk you through everything you need to know about setting up a lithium-ion cell manufacturing plant. We will design the cell, tweak the manufacturing process, figure out logistics, choose the right equipment, and calculate staffing and utilities. We will also map out layouts, predict defects, yield, and throughput, and get into supply chain and scrap management. To top it off, we'll put together a solid financial model covering cash flow, income statements, and more. It will take at least a year to cover all this in detail. It's a really complex topic. And while I can't promise I will upload videos on a strict schedule, let's take that first step together today and see where this goes. I want to dedicate this series to the amazing folks I've met in India. You've really changed the way I see the world. We will start our journey from rethinking what battery is and how it behaves in a circuit. Everyone is familiar with the infographics like this one, where batteries are used to help explaining the Ohm's law. So, let's revise this knowledge by doing two simple exercises. Here we have a circuit consisting of a battery, a voltmeter connected in parallel with the circuit, an ammeter, a resistor, a diode, and a switch. All components, except voltmeter, are connected in series. The measured voltage of the battery is 4 volts. From the datasheet we know that the voltage drop across the red LED diode is 2 volts, and the desired current is 20 milliamps. Now, let's calculate required resistance of the resistor. According to Ohm's law, the current flowing through the resistor is proportional to the voltage drop across it and its resistance. In this case, we know that the current is 20 milliamps. We also know the voltage drop. Therefore, we must rearrange the equation. Now we see that the resistance equals the voltage drop divided by the current. In this case, the voltage drop across the LED diode is 2 volts. So to balance the supply voltage of 4 volts, the resistor must also drop 2 volts. As a result, we need a 100 ohm resistor. As simple as that. Now, let's consider a similar circuit, but this time we'll remove the resistor and replace the diode with an adjustable resistor, specifically a potentiometer. In this case, we still have a power supply of 4 volts, but now we only have one passive component, so the entire 4 volts will drop across it. Next, let's calculate the current based on the constant voltage drop and adjustable resistance. If the resistance is set at 500 ohms, the current will be just 8 milliamps. However, if we decrease the resistance to 100 ohms, the current will increase to 40 milliamps. Setting the resistance to 30 ohms will result in a current of 133 milliamps. And if we reduce the resistance even further to just 2 ohms, the current will surge to an astonishing 2000 milliamps. That's a staggering 2 amps. Remember, even though the resistance and current are changing, the voltage remains constant at 4 volts. That's a very important observation here. We have done some calculations. Now it's time to observe how the parameters behave in the real circuit. Here we have a circuit that is a combination of the two from the previous exercises. The circuit consists of a power supply, a voltmeter, an ammeter, a potentiometer, a diode, a resistor, and a switch. The voltage at the power supply is adjusted to 4.06 volts. After switching the power on, we observe that the voltmeter reads 4.07 volts. The 10 millivolt difference is due to the limitations of lower quality multimeters. However, this level of accuracy is sufficient for our experiment. Furthermore, I want to show you experiments with the cheap equipment so that you won't get confused while doing your own experiments. Now, let's close the switch. We notice that the voltage on both the power supply and the voltmeter remains unchanged, consistent with our earlier exercises. Current is now flowing through the circuit. The power supply indicates 21 milliamps, while the ammeter shows 30 milliamps. For our purposes, we will rely on the ammeter reading, despite its lower accuracy. Next, we increase the current by reducing the resistance on the potentiometer. The current rises to 100 milliamps, and we observe a 10 millivolts drop on the voltmeter. As we further decrease the resistance, the current reaches 360 milliamps, and the voltage on the voltmeter drops even more. Throughout this, the voltage at the power source remains constant at 4.06 volts. Interestingly, our voltmeter behaves differently than anticipated based on previous exercises. To verify if this is not an error, let's turn the switch off. The voltage returns to 4.07 volts. While the switch back on, the voltage again drops to 4.04 volts. Let's try to explain this phenomena. We start from excluding the LED diode and its resistor from our analysis, as their impact is negligible when the potentiometer's resistance is low. Looking closely at our lat setup, we see that between the power supply and the voltmeter probes, there are connector wires. These wires have their own resistance, which we must consider if we want to achieve accurate measurements. For this example, we'll assume that the wires and alligator clips are of poor quality, resulting in a resistance of 25 milliohms. We'll keep the power supply set to 4 volts to compare our calculation with previous results. Now we will treat these wires as a single resistor in series with potentiometer. Comparing this to previous calculations, we can observe that as potentiometer's resistance decreases, the influence of the wire resistance increases. Now let's revisit Ohm's law. The voltage drop across the wires is proportional to the current flowing through them and their resistance, in our case 25 milliohms. If the current is just 8 milliamps, the voltage drop is mere 0.2 millivolts. But as the current increases, the voltage drop can reach nearly 50 millivolts. This assumption can be checked very easily. We just need to connect our voltmeter directly to the power supply. Let's do that and see what will happen. And there you go. No matter what we do with potentiometer or the switch, the voltage on the voltmeter remains constant. This means that our logic is correct. If we take those minor adjustments into account, we can also see that so far our calculations and observations are in line with the Ohm's law cheat sheet which I shown on the very beginning of this video. This is also very important. You might think why I am focusing so much on this detail, but as you will see with the next examples, this will prove to be very important. In the Ohm's law cheat sheet, the voltage source is represented as a battery. However, I've intentionally switched it to a lab power supply. So far, this change hasn't impacted our calculations, which would lead us to conclusion that the circuit behaves consistently regardless of the voltage source. To test this hypothesis, let's connect a bank of 7 capacitors in parallel as our power supply. Now we can see that the circuit behaves completely differently. Merely closing the switch leads to instant drop of voltage by 150 millivolts. What is more, the voltage does not stabilize, but it keeps going down. Note that lowering resistance on the potentiometer leads to voltage collapse by more than 1 volt. Even the blue LED turned off. We can clearly state that the type of a voltage source has an impact on the circuit. But what actually had happened in this case? Charged particles interact with one another through the phenomenon known as electrostatic force. The force is proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them, as well as factor of 4 pi epsilon 0 epsilon r, where epsilon 0 is the electrostatic permittivity of free space, and epsilon r is the dielectric constant of the material involved. Like charges repel each other, while opposite charges attract. For air, epsilon r is very close to 1. So what happens when one electron gets near another? Each electron carries a charge of 1.6 times 10 to minus 19 in coulombs and has mass of 9.1 times 10 to minus 31 kilograms. Under the influence of electrostatic force, an electron will accelerate in proportion to the force acting on it and inversely proportional to its mass. This results in the electron gaining momentum and kinetic energy. Since the electrostatic force is inversely proportional to the square of the distance between charges, attempting to squeeze more electrons into a confined space increases repelling force. As the distance between two electrons approaches zero, the repelling force escalates toward infinity. When dealing with more than two charges, we employ the superposition principle to determine the resulting force. This involves adding all the individual forces acting on a given particle from the other charges. Because force is a vector, we perform vector addition. For example, even though both Q6 and Q2 are negatively charged, Q6 will accelerate towards Q2 due to the influence of the other charges. However, as the particles rearrange, the forces continually change, ensuring that Q6 will never physically touch Q2. As their separation decreases, the repelling force would rise to infinity. Now let's return to our capacitor. The potential from the power supply compacts the electrons together. Meanwhile, the electrons behind the open switch are evenly distributed, resulting in no voltage between VCC and GND wires at that point of the circuit. The wires can only store a limited number of electrons, which is where a capacitor comes into play. A capacitor consists of two conductive plates separated by dielectric barrier. For simplicity, we can assume that these plates can hold significantly more electrons than wires. Thanks to the dielectric, we can position the plates closer together, allowing us to store more charge in a given space. The capacitor's capacitance, measured in farads, represents the amount of charge stored on the plates in coulombs and the voltage across them in volts. When we close the first switch, the potential from the power supply drives electrons into the unoccupied section of the circuit. This process causes one plate of the capacitor to become negatively charged as electrons accumulate, while the other plate loses electrons. Thus, an electric field develops between the plates, which results in a voltmeter reading of 5 volts, the same as the initial voltage from the power supply. Once we disconnect the circuit from the power supply, the driving force from the power supply disappears. The electrons rearrange slightly, leading to a drop in voltage. However, as they reach a new equilibrium position, the voltage stabilizes. Next, we'll keep the power supply switch open and close the second switch. This allows the electrons from both plates to flow freely towards equilibrium. If the circuit had zero resistance, this rearrangement would happen at the speed of light. However, due to the circuit's resistance, the electrons flow more gradually, attempting to bring the voltage between the plates down to zero. As electrons move from one plate to the other, we see the voltage decrease, initially quickly, then more slowly. It is important to note that the direction of the electron movement is opposite to the direction of the conventional current flow. This is a result of the convention that current flows from higher to lower potential, while electrons actually flow from lower to higher potential. The electric current vector, meanwhile, aligns with the electric field vector. Finally, let's compare the lab power supply with the capacitor. While both have the same electric charge, the power supply appears to hold an infinite amount of it. This brings us to the intriguing question about how this magical device functions. We will explore that soon, but first, let's connect a battery to the circuit. Finally, we are ready for that. We've now connected the battery to our alligator clips instead of the lab power supply. The initial voltage reads 4.06 volts. When we close the switch with the potentiometer set to maximum resistance, we observe a voltage drop of 10 millivolts. In contrast, when using the lab power supply, there was no voltage drop at all. With the capacitor, the drop reached as high as 150 millivolts. After this initial 10 millivolts drop, the voltage stabilizes, which is quite different from the continuous drop we saw with the capacitor. Now, let's decrease the resistance on the potentiometer. With a current of 410 milliamps, we notice that the voltage dropped by 110 millivolts, but it stabilizes as well. Just to compare, the lab power supply only exhibited a 30 millivolts drop under similar conditions. Since the battery is connected to the same alligator clip previously used for the power supply, the resistance of the wires can't explain this difference. So what could be causing this phenomena? Let's take another look at the circuits powered by the capacitor and the lab power supply. Here we focus on charge carriers, which are primarily electrons. These electrons flow exclusively through the circuit, and it's important to remember that the dielectric in the capacitor prevents electrons from moving between the plates except through the circuit itself. However, the battery operates differently. Instead of merely storing electrons, it also holds compounds formed with ions. This unique structure reduces the electrostatic forces at play, allowing us to pack more charge into a confined space. When we close the circuit, electrons separate from ions and move through the circuit to do useful work. Meanwhile, the ions also travel to the opposite side, but their movement occurs internally within the cell itself. This introduces both the external resistance of the circuit and the internal resistance of the cell. This internal resistance is why we observe a greater voltage drop with the battery compared to the lab power supply. We will dive deeper into the implications of this phenomena in the future videos. But for now, let's cover our final topic. As electrons detach, we are left with freely positively charged ions, cations, that move from one side of the cell to the other. Since cations are positively charged, they move in the same direction as the current vector. However, if we analyze the electric field and current vectors within the cell, we notice they point in opposite direction. Electric current flows from the lower to higher potential, which seems paradoxical. To facilitate the movement of charges from lower to higher potential, there must be an additional force that exceeds the electrostatic force. Indeed, within the battery, this force exists and is referred to as electromotive force, EMF. We will explore EMF in more detail in our next video, but for now, keep in mind that when dealing with electromotive force, our understanding must stretch beyond basic electromagnetism. This is why it's oversimplistic to consider batteries as mere electrical components in a circuit. Now let's summarize what we've covered in this video. The battery is a non-linear power source with its own internal resistance, making it unsuitable for simple applications of Ohm's law. Capacitors store energy in the form of an electric field. Due to the inverse square relationship between electrostatic force and distance, it's tough to pack a lot of electrons in a confined space. Thus, capacitors have lower energy density than batteries. However, capacitors have no internal resistance, allowing electrons to move solely through the circuit, resulting in maximum currents that are many times greater than those of batteries. When multiple forces act on charged particles, we use the superposition method to determine the resultant force. In batteries, in addition to electrostatic force, there is also electromotive force, which drives their functionality. Understanding electromotive force requires broader knowledge beyond just electromagnetism, which is why many electricians find batteries to be unpredictable and volatile. I hope this video has helped clarify some of the fundamental concepts. While it may seem like spending nearly 30 minutes on just a few ideas is excessive, my goal is to ensure we are all on the same page. In the next video, we will take a deeper dive into electromotive force. Thank you.